Hello, my name is Oscar, and today we're going to be working on examination for chapter N and chapter 12. Chapter 11 and 12, my bad. Examination. Examination for problem 3. So to start with this examination, part A and part B are the same problem. So we're going to write right here, part A and B. So for the first part, for part A, or for the whole problem, we have a copper wire. For part A, we need to find the tensile stress of on the wire, and for part B, we need to find what is the magnitude of the force on either end. So for part A, we're gonna have the next values, which are the radius. Radius is equal to 3.3 millimeters. That's radius. We also have the Young's modulus of copper, which is equal to 11 times 10 to the power of 10 pascals. So Young's modulus or modulus of copper. And we have the strain or stretch that is going to be equal to 5.0 times 10 to the power of -3. So a strain or stretch. So now to start with this exercise, we're gonna find, for part A, we need to find the tensile stress. So we're gonna use the next formula, which is tensile stress is equal to the Young's modulus of copper. So E times the strain, which is gonna be this right here. So when we plot the numbers, we have 11 times 10 to the power of 10 times 5.0 times 10 to the power of -3. So the tensile stress is going to be equal to 5.5 times 10 to the power of 8 pascals. So this is the solution for part A. Now for part B, so we need to find the force, and to use force, we need to find the area of a circular wire. So the formula for area is gonna be equal to area equal to P times radius to the power of 2. Our radius is in millimeters, so we have 3.3 millimeters, and this is going to be equal to 3.3 times 10 to the power of -3 meters. So now area is going to be equal to P times 3.3 times 10 to the power of -3 to the power of 2, and we're gonna have the result is gonna be 3.42 times 10 to the power of -5 square meters. So now that we have area and we have the tensile stress, we can find the force on each end. So we're going to use the formula. Force equals to tensile stress times area. So force is gonna be equal to 5.5 times 10 to the power of 8 times area. So 3.42 times 10 to the power of -5. So the final answer for part B, it's gonna be 1.88 times 10 to the power of 4 newtons. We can round this to 1.9 times 10 to the power of 2, and this is gonna be the answer for part B. So now for the next two exercises, we have part C and D, which is the same problem, but two different parts. So for this exercise, we have an aluminum cylinder, and the first question, or the first value that they are asking is what is the compressive strain of the cylinder? That's for part C. And for part D, by what distance does the cylinder's height decrease as a result of the forces on it? So our given values, we have the radius of the cylinder, which is equal to 3.1 centimeters, which is equal to 3.1 times 10 to the power of minus 2 meters. We also have the height of the cylinder, which is equal 82 centimeters, which is also equal to 0.82 meters. We can also say that the height is represented by the letter L. And we also have the force applied, or the applied force. So this is going to be equal to 3.2 times 10 to the power of 4 newtons. And we have the Young's modulus of aluminium, which is equal to 7.0 times 10 to the power of 10 pascals. So now we're gonna start finding the area. So area is gonna be equal to P times radius to the power of 2. This is gonna be equal to P times 3.1 times 10 to the power of -2. So the area, it's gonna be equal to 3.02 times 10 to the power of -3 square meters. Now, we need to find the stress. So we're gonna use the formula right here. Stress is gonna be equal to force over area. And now we have the force is gonna be 3.2 times 10 to the power of 4 over the area, which is 3.02 times 10 to the power of -3. So the stress is gonna be equal to 1.06 times 10 to the power of 7 pascals. Now that we find the area, we were able to find the stress. Now we need to find the strain. So for strain, it's gonna be equal to the stress over the Young's modulus. So right here, E. So we have 1.06 times 10 to the power of 7 over the Young's modulus, that is 7.0 times 10 to the power of 10. So the strain, it's gonna be equal to 1.51 times 10 to the power of -4. So this is going to be the answer for part C. Now for part D. As we say before, they're asking by what distance does the cylinder's height decrease as a result of the forces on it. So our formula right here, this is the formula that we're going to use, the strain times the height. So we have 1.51 times 10 to the power of -4 times 0.82. The result of this operation is gonna be 1.24 times 10 to the power of -4 meters. So this is our answer for part D. Now we're gonna start working on the next exercise. For next exercise, we have part E and part F in the same exercise. We have a sphere. For part E, our sphere is made of lead, and for part F, our sphere is made of mercury. So part E and D. F. Okay, we're gonna start with the given values. So our radius is gonna be equal to 1.2 centimeters, which is equal to 1.2 times 10 to the power of -2 meters. We also have the pressure on the sphere. This is equal to 2.5 times 10 to the power of 7 pascals. And we also have the volume of the sphere. So the volume is gonna be equal to 4/3 times P times cubic radius. For part E, our sphere is made of lead. So the bulk modulus of lead is gonna be B equals to 4.7, 4.1 times 10 to the power of 10 pascals. This is for lead. And now we have, for part F, we have mercury, which is gonna be equal to 2.7 times 10 to the power of 10 pascals. Okay, so for part E, we're gonna compute the volume. So we're gonna use the formula for volume. So we have volume, it's equal to 4/3 times P times cubic radius. So this is going to be equal to 4/3 times P times the radius, which is 1.2 times 10 to the power of -2. And when we do the operation, we have volume equal to 7.24 times 10 to the power of -6 cubic meters. And now we have to compute the volume decrease. So we have volume decrease is equal to negative, we have, okay, the pressure, the Boyle's modulus times volume. So we have, this is gonna be equal to negative 2.5 times 10 to the power of 7 over 4.1, because we're doing the lead, so 4.1 times 10 to the power of 10 times the volume that we just find it, that is 7.24 times 10 to the power of negative 6. And when we do the operation, we have negative 4.4 times 10 to the power of negative 9 cubic meters. But like this is a magnitude, we can say that this is, instead of being negative, it's positive. So 4.4 times 10 to the power of negative 3 cubic meters. So this is gonna be the answer for part E, a sphere made out of lead. And now we have to do like the same calculations, but instead of doing it for lead, we're gonna do it for mercury. So for part F, I keep saying D. For part F, we're gonna use the same formula to compute the volume decrease. So this is going to be negative, or we have the pressure, we have the Boyle's modulus, and we have volume. And this is going to be equal, to 2.5 times 10 to the power of 7 over the Boyle's modulus for mercury. It's going to be 2.7 times 10 to the power of 10 pascals times the volume. The volume was 7.24 times 10 to the power of negative 6. And when we do the operation, we have that this is equal to negative 6.7 times 10 to the power of negative 9 cubic meters. But again, like this is a magnitude, we can say that this is positive. So 6.7 times 10 to the negative 9 cubic meters. So this is the answer for part F. And now for the last exercise for problem number 3 for chapter 11 and 12, part G. We have a cube and we need to find what is the resulting shear displacement. So for this, part G, our given values, force is equal to 4.2 times 10 to the power of 4 newtons. We also have the shear modulus of brass. We're going to use the letter G. 3.5 times 10 to the power of 10 pascals. We have the length, so the cube side length. So this is going to be L equal to 2.5 centimeters, which is equal to 2.5 times 10 to the power of negative meters. And we have the formula for cube, or the face. This is the length, square length. And now we're gonna start with this. So the area of the face of it's gonna be the length. So we had 2.5 times 10 to the power of negative 2, and this is gonna be equal to 6.25 times 10 to the power of negative 4 square meters. Now we need to compute shear stress. So we have the formula. So the force, let's say this is force. So this is going to be equal to 4.2 times 10 to the power of 4 over this was the shear modulus of brass, which was 3.5 times 10 to the power of 10. So the shear strength is gonna be equal to 1.92 times 10 to the power of negative 3. Now we need to find the shear displacement. So now we need to find the shear displacement. So for this, we're gonna use the strain, and we're gonna use the length. So our formula is gonna be shear displacement and the length. So the x is gonna be equals to 9.92 times 10 to the power of negative 3 times the length that was 2.5 times 10 to the power of negative 2. When we make this calculation, our final result is gonna be 4.8 times 10 to the power of negative 5 meters. So this is the answer for part G. And with this, we have finished the examination for chapter 11 and 12. Thank you.